Okay, so here's a quick review of Module 1. So the first thing we learned in Module 1 is actually a review of last semester. And that is that the component of the force in a given direction is equal to minus the derivative of the potential energy in that direction. So here I have the x component of the force is minus du by dx, and if I wanted to know the y component, it would just be minus du by dy. So that's true for anything that has a potential energy function. Next we learned about the electric potential V, which is a scalar field, and it has units of volts, and if you have multiple potentials, they obey the principle of superposition, so you can add them together. The electric potential for a point charge is just equal to 1 over 4 pi epsilon naught, this is just a constant, times the charge Q divided by R, where R is the distance between the charge and the point where you're trying to calculate the potential. And this coefficient is sometimes called K for short. We then learned that the electric potential energy of a charge Q in an electric potential V is just the charge Q times V. And finally we learned that batteries are things that supply and sustain a difference in potential. So if I have a 9-volt battery, that battery makes sure that there's a difference of 9 volts between the two terminals. So this is all Module 1. So you could do everything we did in Module 1 from just these facts, but I'm going to keep going a little bit. So using the relationship between force and potential energy and the electric potential for a point charge, we can calculate the force due to a point charge on another point charge. And that's known as Coulomb's law. So F is just the derivative of the electric potential energy with respect to R. So if we plug U in, we have minus the derivative of Q times V. Q is a constant, so we can pull that out of the derivative, so we just have minus Q times the derivative of V. And if we plug the potential for a point charge in for V, we have a bunch of constants times 1 over r, so we just have those constants times the derivative of 1 over r, and the derivative of 1 over r is minus 1 over r squared, so the two negative signs cancel and we get 1 over r squared. And so I've put absolute value signs around the q's, and that is because you can't use Coulomb's law to find the direction of the force. So for example, if I have a positive charge right here, and I put a negative charge a distance r to the right, and I want to know what's the force on the negative charge. That force is going to be in this direction. If I put the negative charge to the left, a distance r away from the positive charge, the force will have exactly the same magnitude. I'll still have a plus q and a minus q on top, but the force will be to the right instead of to the left. So, this would give you exactly the same thing for each of these, but the force is in the opposite direction. So you should always figure out which way the force is pointing by looking at the charges. And then finally we talked about calculating potentials for continuous charge distributions. So here I have a blob of charge continuously distributed, and the total charge is Q. And I want to know what the potential from this arrangement of charge is at point P. So what's the potential at point P? So how can I do that? Well, I can break the continuous charge distribution up into little tiny pieces of charge. So I can treat each of these as a point charge. So I can treat this as a point charge with charge dq. So that's just an infinitesimal piece of charge, dq. And then I'll have a distance from P to dq, so I'll have an r. And I can do the same thing for each one of these little pieces. So each little contribution to the electric potential is a little dV, and each one of those contributions comes from a tiny piece of charge dq. So this is just, the potential for a point charge, except instead of a q, I have a dq because it's just a little piece of this. And then if I add all those up, because potential obeys the principle of superposition, adding all those up is just like taking an integral. So if I take an integral of this side, I just get v, and over here I just integrate the dq over r. And so in class we calculated the potentials for continuous charge distributions like disks, rings, lines, etc. And that's all of Module 1.